like somebody who would just randomly say 20?
Lesson 75. Continuity of functions. How about we talk about continuity of functions? Continuous. Okay? So, we are specifically talking or learning about the intermediate value theorem today. In calculus, there are lots of theorems. Okay? There are theorems that are important to know the details of. This is one of them that you can use within problems to prove things, to show things. So it's good to know all the pieces here. So I'll read it and then we'll dissect it. If f is continuous on the closed interval a to b, and n is a number between f of a and f of b, then there is at least one number c between a and b inclusive for which f of c equals n. Interesting, huh?
Yeah.
Makes all the sense in the world, right?
That just took my mind for a moment.
Okay. And I will tell you, even as a math person, that is a blur to me until I dissect it.
It's just a lot.
It is. It's a lot. It's the understanding. Okay.
So n is the y value for c.
Yes. Yes. Okay, so, first of all, key piece of information. You see the word continuous, yes? This intermediate value theorem means nothing if you do not know the function is continuous. If they don't state the function is continuous, or if you don't, some functions we know are continuous just based on what they are. We'll talk about that as we go. Or they may tell you the function is continuous. But if you don't know if the function is continuous we're talking about, or if they don't tell you it's continuous, intermediate value theorem cannot apply. Okay, so that whole idea of being continuous is very important for some of these theorems. Intermediate value theorem is one of them. So, if f is continuous, so as we look at this picture, right, it's continuous. There's no jumps, there's no gaps, there's no holes. It's continuous. On the closed interval from a to b. So, meaning 2 and 8 are essentially my a and b values here. Okay, so if f is continuous on the interval from a to b, so from 2 to 8, and n is a number between f of a and f of b. So keep in mind, if a and b are my x values, then f of a and f of b represent my y values. And so it's the idea that if a is 2, then f of a is the y value over here. If b is 8, then f of b is that equivalent y value. Do you see how I drew those lines in there as a visual? And I can zoom this in so you guys can see more. So this is saying if f is continuous on this interval from a to b, closed interval, so a and b included, n is a number between f of a and f of b. That means what is n in this picture?
42.
That 42 is what they're saying. Okay? So n is a number between f of b, and there's at least one number c between a and b, for which f of c equals n. Meaning, so if this is n right here, where's my c value have to be? Down from here. And so the idea that f of c is equal to n. Okay. In short of it, if I can try and put it in words for you. Okay. If you have if my function is continuous, and I have two x values, then thus there are two corresponding y values, right? That's saying between the two x values, there's a value that equals something that's between the two corresponding y values. Have I made it make sense yet? I mean, that's kind of what my drawing says. Okay, I've got these x values, I've got the y values they equal. So there's some value between the x values that equals some value between the y values. That is guaranteed to happen as long as we know this function is continuous on this interval. Okay? So that's the idea of the intermediate value theorem. Okay, let's look at some applications of intermediate value theorem as we go along today. Prove. So you see the word prove. That f of x equals x cubed minus 5x plus 2 has a root between x equals 0 and x equals 1. What do I mean root? X-intercept. I was going to use the word 0. Are you okay if I use the word 0? Okay. So when we talk about a root, we are talking about an x-intercept. We are talking about a 0, a place where x equals 0, right? Okay. So we are trying to prove that this function has a root between x equals 0 and x equals 1. So we're trying to prove that this function has to cross between x equals 0 and x equals 1. Has to cross the x-axis. So I guess if you want me to put x-intercept on here as well, I can. Okay. Obviously, we just talked about intermediate value theorem, right? So we're using that idea. First thing we need to discuss if we're going to talk intermediate value theorem is what?
You plug it in, you get y values.
Before I even do that, though.
Is
Is it
it continuous?
continuous? F of x equals x cubed minus 5x plus 2. What's an x cubed graph? Some kind of squiggle, right? Starts low, ends high, maybe curves around in the middle, right? Okay. Is there any denominator that would cause me to maybe have a hole in this equation or anything? Okay. So what I'm going to use for this one is just by definition that this is just a basic polynomial, it is continuous. Okay, just if this was f of x equals x squared and some stuff, or x and so, even if it was x is 7, if it's just terms added and subtracted, that's a polynomial, it's going to end up being continuous. It's when you start getting denominators and places where x can't equal certain things that it's not going to be continuous. So first thing I'm going to write is that f is continuous. And this is something, if you're doing an open-ended problem on a calc exam, you can't just, it's never just assumed that f is continuous. Either it has to be stated in the problem, or you have to state it with reasoning. Okay, so that's what I'm doing here. F is continuous because it is a polynomial function. And to any math person, that is a perfectly good explanation. Okay? Okay. We want to show that this graph, that this function has a 0, an x-intercept, a root between x equals 0 and x equals 1. So, in order to do this, we need to know what's happening at those two endpoints, yes? Those are kind of the endpoints. So, Jack, this is where you said find what the y values are there. We know the x values. The x values are 0 and 1. So let's find the y values. So let's find f of 0. And let's find f of 1. So if we find f of 0, 0 cubed minus 5 times 0 plus 2. F of 0 is 2. If we put in 1, 1 cubed minus 5 times 1 plus 2. F of 1 is negative 2. Okay. So if f of 0 is 2, that's left to right 0 and up 2. f of 1 is negative 2, so that's right 1, down 2. If this graph is continuous and those dots are connected, is my graph going to cross the x-axis? And yes, it has to. I'll give you a little visual if you need the visual here.
So if it changes the sign between those two, then that's when you know if it's a root between.
Yep, that would work. So if I graph 0, there's 0, 2. Here's 1, negative 2. I don't care what the rest of the graph looks like. But this is a continuous function. So what's happening between those 2 points? It has to connect somehow. Okay? I don't know how, but it has to connect somehow. Because as my graph moves left to right, it's going to connect them. Now, what just happened in this? We crossed the x-axis. So we have a root. And again, it was because it moved from being a positive y value to a negative y value. So this is, by intermediate value theorem, we have just proved this. So I'm going to say by IVT. IVT stands for intermediate value theorem. That is an acceptable abbreviation to use even on an AP Calc exam. Okay? So by IVT, a value, I'm going to say a value C between x equals 0 and x equals 1 exists such that f of c equals 0. Putting it in words is probably the hardest part. Okay, when you, and I know I haven't really showed you guys much in the way of examples yet, but when we start looking at more open-ended, free response problems. Okay, a free response problem, you'll have 6 free response problems total, and they range anywhere, they're usually about 4-part problems, an A, a B, a C, a D, and they're big parts. So like this could be an A, B, C, or D part. Okay, it also could be multiple choice type thing, but it's hard to do something like this multiple choice. The picture would not be necessary, but stating that it's continuous, showing these 2 values of a positive 2 and a negative 2, and then putting it all together and summarizing would be an appropriate answer. Okay? I'll be honest, it's a struggle of mine to get that all in there together. But those are the things that would earn you full points. Okay, questions there? Okay, we've talked about these before, I believe. At least in my head we have. Different ways a graph can be discontinuous or not continuous, right? Okay. And so, possible discontinuities. You could have where the graph totally has a break, right? What they call a jump, or it jumps from one value to next. You could have where a graph appears to be continuous, but there is a removed point, an extra point. Okay, so in technicality, is this graph continuous? No, because there's that extra point. You could also have a hole where, again, is this graph continuous? Almost, but not quite, because technically you have to lift your pen or pencil for that little dot. Yes?
So on a calculator, sometimes we'll look up things and it stops and then it goes again, but it's actually continuous. And the calculator just messed it up. How do we distinguish that between an actual discontinuous?
Checking to see if the x and y value, like if the y value exists at that point would be the key. Okay, I mean, I'd have to look at a specific example of what you mean there, but you do have to, graphing calculator error there, that is definitely a thing, okay? And so, but checking to see if the y value exists is the key. The thing is, unfortunately, with holes this small, you have to be able to see it in the equation because a lot of times you can't see a hole like this on your calculator. But even then, there's times I haven't even been able to find it when I zoom in, but you might, but you have to know what you're looking for. But remember, when do holes happen? Holes happen when my denominator equals 0, and it's a factor that cancels. So like if my denominator equals 0 and I don't have an asymptote there, that means there's a hole there of some sort. So, okay. Now, definition of continuity at a point. Okay. On that polynomial, we could just state it's a polynomial. We know it's going to be continuous. Definition of continuity at a point. This is how, if you need to show that something is continuous. These are the pieces you have to show. If something is if by definition, a function f is continuous at a point C, if f exists at C, and, so notice this says the limit from the left, so this is the limit as x approaches C from the left, is equal to the limit as x approaches C from the right. So in other words, the idea of the limit from the left and the limit from the right, they have to equal the same thing. And they have to equal what f of C is. So they have to equal what that y value would be. Okay? So if I compare it to up here, like both examples 2 and 3, my limits are the same from both the left and the right, yes? Because they're meeting at one point. Okay? However, this part of if equals f the limits equal f of C, this one does not equal f of C because f of C is right here. Like if you're thinking of this being, like this is my C value here. Right here, limit equals that, they equal the same thing, but I need that f of C to be in this hole, and it's not. Over here, same thing. Limit from the left, limit from the right, my graphs meet at the same spot, but saying it equals f of C means that point exists right there on the graph. Does that make sense? That's the idea of what we're trying to say. Limit from the left equals limit from the right and equals that value at that point. Okay, those are the three pieces you have to show if you're proving something is continuous. Yeah, we'll talk about it. We have an example or two we'll talk about. Okay. So 1, 2, 3. Definition of open interval continuity. A function f is continuous on an open interval, a and b, if it is continuous at every point on the interval. What do we mean by open interval? Just means the endpoints are not included. So this is your parentheses, where it's to a and b, but does not include a and b. So continuous on the interval if it's continuous at every point on the interval. Closed interval continuity. A function f is continuous on a closed interval a to b if it is continuous at every point between a and b, and if it is defined at both a and b. Okay, so in order for it to be continuous on that whole interval, those endpoints have to exist. And so notice here, the limit as x approaches a from the right has to equal f of a. The limit as x approaches b from the left has to equal f of b. So just the has to exist down there. Okay, again, we're going to look at some examples here. Speaking of example 2. Let's work to apply this intermediate value theorem and the continuity idea. Suppose the function f is defined on the interval 1 to 3. F of 1 equals 1. F of 3 equals 7. Does a number c exist such that 1 is less than c is less than 3, so such that c is between 1 and 3, such that f of c equals 3. So we're thinking intermediate value theorem, right? Okay, that's what this is trying to talk about. They tell us the function is defined on the interval from 1 to 3. Okay, so the function exists on the interval from 1 to 3. They're telling me the endpoints. One endpoint, f of 1 equals 1. The other endpoint, f of 3 equals 7. Does a number c exist between 1 and 3 such that f of c equals 3?
since it doesn't say that the function's continuous.
Yep. We can't guarantee anything. Could a point possibly exist? I mean, this is intermediate value to a t, in that my x values. You guys see what's happening here? It was 1, 3, right? They're saying there's a point at 1, 3. They're saying there's a point at 3, 7, right? And so, if it had stated it was continuous, then I know my graph does something here, right? If C is a value between 1 and 3, so if C is somewhere here, could it possibly have a value of, what was it, 3? No. Such a f of C, oh, I messed this one up, didn't I? It was 1, 1. That makes more sense. So is it possible that there would be a value at 3?
It could.
If, this would be a perfect intermediate value theorem, if they stayed continuous. Do we know anything about this function and decide if it's continuous? No, they didn't give me an equation that I can say, oh, yep, that makes sense, that's continuous. They just said, suppose that f is defined. So, does a number C exist? Maybe yes, maybe no. I'm going to say, not necessarily is my phrasing here. In other words, I'm not going to say no, but the point is, we don't know. And my explanation of the function was not defined to be continuous. The function was not defined to be continuous on the interval 1, 3. So, f of C equals 3 is not guaranteed. If they had thrown the C word in there and said continuous, it would have been a prime example of intermediate value theorem. Unfortunately, they didn't make that easy for us. Okay. Example 3 when you're ready on the back side. You leave your notes at home. I just now realized that.
I've had to do that 1 or 2 times.
It's annoying, I know. I guess the question is, did you guys all have your notes with you at home yesterday? Because it's also annoying if you don't have your notes with you, I'm sure. Or do you guys just take your notes home every day no matter what, pretty much?
Sometimes if I'm feeling first close to it.
Okay, example 3. Suppose f is a function that is continuous on the closed interval -1 to 3. Which of the following could be a graph of f? Okay, so, key definitions. What'd you guys see? Continuous, closed interval.
So does that mean it has to be D?
Has to be D because D is the only one. Yeah. I mean, they're all somewhat continuous.
Except for C, right?
Yeah, well, but even that's at the end point.
Oh, I need to see it.
Yeah. They're all essentially kind of continuous on the open interval. Because they're all continuous on the open interval in that the endpoints don't matter then. But the only one that has the good endpoints are D. So because it said closed interval. You okay with that? Moving on. Let f be a piecewise function defined as follows. F of x equals the absolute value of x plus 3 when x is less than 1, and ax squared plus bx when x is greater than or equal to 1. Find values of a and b such that f is continuous on the interval negative infinity to positive infinity. So this is a piecewise function. When x is less than 1, my graph looks like one thing. When x is bigger than 1, my graph looks like something else. We're trying to find values that make A and B so that my graph, those two pieces, join together and are continuous. Okay? My recommendation is let's first think a picture about what we know here. So, what can you guys tell me? Absolute value of x plus 3. F of x equals absolute value of x plus 3.
It's going to be the left plus b plus the 1 point.
Okay. So if we, absolute value of x is a v, plus 3 outside the absolute value takes that v and moves it up 3. So generally speaking, I'll put it in pen in a moment. Generally speaking, there's my absolute value v, yes? But where is that absolute value of x plus 3 defined for? It specifically said when x is less than 1. So that means this graph only goes over to x equals 1. So the graph exists here. And it exists over here. Without thinking I did it. Yeah. Can you guys tell? I put an open circle here. Yeah, why? Okay, it says when x is less than 1. So my absolute value v is going to go all the way up to like 0.9999999, but officially we don't know what the value is at 1. Does that make sense? Okay, and that's because it just said when x is less than 1. Now, okay, so basically this piece of the v doesn't really exist now, right? What's my graph do to the right of 1? ax squared plus bx. So what is ax squared plus bx? A parabola, yes? Now, we don't know exactly what's going on with this parabola. We don't know a and b yet. But think about it. What are some options? My parabola could be curving up, right? Do we know it's curving up? It could be curving down. We don't really know what our parabola looks like at this point. Okay? However, we know it has to connect right here at this point. Yes? So, okay, things to think about. First of all, we are trying to figure this out so that this function is continuous. To be continuous at this point, I talked about 3 things have to happen to be continuous at that connecting point. First of all, the limit from the left. What is the limit as x approaches? What's the x value we need to talk about here? This is at 1, right? As x approaches 1 from the left. Well, which part of the graph are we talking about? When x approaches 1 from the left, we're on the absolute value v, yes? So what is the limit there? As we follow this v and as x approaches 1, what y value is that going to be equal to? 4, because on absolute value v, my graph goes up 1 over 1. So, and if it helps, I mean, basically think that is the ordered pair 1, 4, yes? Okay, so we need the limit from the left to equal 4, which means the limit from the right also has to equal 4, which means the value of that point has to equal 4. Because remember, the limit from the left, the limit from the right, and the value at that point all have to equal 4. So that means, what does ax squared plus bx have to equal at that point? 4. we know ax squared plus bx has to equal 4 when what is true? When x equals 1. In other words, when you have that word pair, 1, 4, we know that has to be true. Okay, so if ax squared plus bx equals 4, when x equals 1, that's when the function will be continuous. What's the equation I can come up with to work with here? If we put in 1 for x, what are we going to have? A plus b equals 4. So what we know is the function will be continuous when a plus b equals 4. Can you come up with a set of values that work? Okay, 2 and 2, 3 and 1, 1 and 3. Does anything say A and B both have to be positive? No. Okay, this parabola could be upside down. A could definitely be a negative value. So my answer when it says find the values of A and B such that make F continuous, my official answer, any values A plus B equals 4. Okay. You could leave your answer like that. If that is just too unsettling to you, you can come up with specific values. So you could say, or A equals 3, B equals 1. Or, if you want to be more creative, A equals negative 7, B equals 11. Do those satisfy the statement A plus B equals 4? Okay, so really there's an unlimited number of solutions here. But the grading key would be that A plus B, your two numbers have to equal 4, or you have to state when A plus B equals 4. Okay? Okay, questions there? Okay, one more. Another piecewise function. Perfect for this intermediate values theorem here. Let f be a piecewise function defined as follows. F of x is x squared minus c squared over x plus c, pretty much all the time except when x does not equal negative c. So that's the only time it's not that. Or it's the only time that it's not that, yeah. The other thing it's defined as is 2c, and that's at the point when x equals negative c. Okay, is x continuous on the interval negative infinity to positive infinity? So definition of continuity again. What has to be true? Limit from the left has to equal the limit from the right, and it has to equal at that point. Let's look at the piece when x does not equal negative c. Let's look at the top piece there.
It's going to be a whole.
So if we look at, okay, good. You guys see where I'm going with this. If we look at this piece right here, the point where x cannot equal c, which is pretty much the entire graph, right? Except for one little point. X squared minus c squared. What do we know about x squared minus c squared? I know the boys saw it. Square root of x squared is x. Square root of c squared is c, and since it multiplies to be a minus, it's a plus minus. X plus c in the denominator. So what can happen here? A factor of x plus c cancels. Okay? And so this is equivalent to x minus c. Guarantee I did not catch that time. You have to be like instantaneous on this one to catch it.
Do you ever get nervous it's not turn off when you start doing updates?
I think I've only ever had that happen like once. So I don't usually get nervous about it, but okay. Okay, so our function is equal to x minus c everywhere except at this point, yes? So what we need to show is the limit, as the limit approaches from the left and the limit approaches from the right, is going to have to equal what it equals at that point. So let's look at the limit as x approaches negative c. And what is a way to call this? X minus c. And honestly, we can look from either way here. But how do you do limits? What have we talked about? You can take that value and do what with it? Plug it in. So the limit as x approaches negative c of x minus c means you can take negative c and put it in for x. So this is now negative c minus c. What is negative c minus c? Negative 2c. What did we need that to equal? If this is going to be continuous, it has to be the same from the left and the right and at the point. What is this at x equals negative c? It's positive 2c. What did we just get? Negative 2c. Does positive 2c and negative 2c equal each other? No. So, is this continuous on the interval negative infinity to infinity? No, because this is not continuous at negative c. So, not continuous at x equals negative c. Now, it should be continuous every place else. If you're asked where it's continuous, you could say, do you remember how to do our intervals here? Yeah. It's continuous on from negative infinity to negative c union, and then negative c to infinity. So it's continuous every place except that one little point. Not that they asked that, but just trying to talk about it. Okay, plan accordingly on your homework. You might need to take an extra picture of homework, but your problem set homework tonight is 75. Saying it again. Okay, 75. When you get to 7 and 8, you're not doing 7 and 8 in those places. You're going to put 9 and 10. You're going to grab those from lesson 74. So you're going to have to flip back to lesson 74. Got it?